first things you learn, so that's why he would skip it. But one of your advantages then is that there's lots of resources for it. You could Google introduction to Mobius function on YouTube, like just check on YouTube, and there, I guarantee you'll find a good lecture somewhere about it, if you're interested. Yeah. All right, so it's about 5, so I guess we can just begin. It's quite interesting because how are we doing with series at the back? Because I actually had a long chat with these two guys on Saturday about series, so I don't know what I should actually cover here. Like, do any of you three have specific questions that we want to work through?
I was just quite happy with the layout that you said in the email. I was just quite happy because I didn't listen for whatever.
Okay. Okay, and I guess maybe some people will watch the recording, so we can just kind of talk through.
And also, I wouldn't mind maybe going through the test a bit more.
Test, okay. Yeah. Anything specific from the test? I don't have a copy here with me. But yeah, that's fine. We can do that.
Yeah, just more going over like that question 1.
Question 1?
Yeah, okay. the whole proof. And like, because I honestly did not understand it that well.
Okay. Gozo, do you have any questions from the test, question 1, or any other questions in the test?
The only question I struggle with is on the test.
Is part C, part C of question 3 maybe?
Yeah,
or 4 or something, I can't remember which one. Okay, let's just take a look. Do you have any questions you want to talk about from the test?
Not really.
Not really, okay. All right, so let's see. Oh, it was 2C that you were...
Yes. I failed to have a common example.
Yeah, that one's a bit...
Because also that's, I tried the rational numbers, like pi plus pi, but this is still rational, like irrational numbers are like pi plus pi, like...
Yeah, so there is a counterexample, but if you don't see it, then it's a little bit harder to think about.
So remember, I was like, oh...
Yeah, what?
Do either of you have any questions you want to talk about from the test?
From question,
From the test, yeah.
Can we go through that?
Oh, which one? Question 1?
Yeah.
Yeah, okay, someone else also asked that we kind of discuss question 1.
And then this limit,
Okay, we could maybe just do one more of those. All right, so maybe we'll try and do it like this. Why don't we try do like say half an hour of the test and maybe like an hour on series, and if we find that we want to do more of the test, then we can do like maybe 45 or something like that. But we should feel good about tutorial 6 as well. We want to be there. We want to say I can do everything in tutorial 6 and it's not a problem. Yeah. I'll write up the questions as well. It's the one we talked about on Saturday.
Yeah.
Okay. All right. Maybe I'll wait for her. But we were going to talk about question 1. Perhaps I should write parts of the question up. I don't know if everyone has this paper, so let's do that. All right, so I'm just going to do like a little test recap, or test, what's the right word I'm thinking of? Sorry, I'm a little tired, so we'll just go with recap. Okay. And we're going to look at question 1, which is this big long question with lots of different parts, where the purpose was to prove that there exists a real number where if you square it, you get 19. In other words, there's a square root of 19 somewhere.
Yeah, what are the conditions for existence? Just like, so why, like how much?
So what happens in this proof is they want to use the completeness axiom, which is telling us that every set that's bounded above has the least upper bound, every set that's bounded below has the greatest lower bound, and they want to use that to show that such a number exists that is equal to the square root of 19. And yeah, so I mean that's sort of the approach of this. Like by constructing a clever set, can we use the completeness axiom to show that such a number exists? I don't know if I can give you, I'm not sure I understand your question perfectly, but I don't know if I can give you a general rule for how to like construct to show that any number exists, depending on what we're looking for. But certainly the completeness axiom is inherently linked to the existence of these numbers that are fundamentally different from the rational numbers. Okay, that's kind of how we get these other numbers. It's one of the ways. So you might imagine, let me put it this way. Suppose you could write out an entire proof that shows that the square root of 19 is a real number. There exists this number like this, and you didn't use the completeness axiom anywhere. And you didn't use anything that was implied by the completeness axiom or equivalent to the completeness axiom. So you only used kind of arguments about inequalities and arguments about the field operations like adding and subtracting. Then I would be very suspicious because you basically kind of showed that you could only use things that were related to the rational numbers to show that there's this number that is like inherently not a rational number. So somewhere in there we expect to have to use the completeness axiom, but maybe in a more advanced setting we might find something that is kind of equivalent to the completeness axiom.
So, so the thinking is then maybe that like we're going to take this property of the natural numbers and then like make a set and then
remember, so completeness axiom, real numbers, right?
Yeah.
This is this about, yeah. So yeah, so in this case the idea is, well, I know that this number, or I maybe have a feeling that I need to use the completeness axiom to show the existence of this number. And since the completeness axiom is like, linked to this idea of like greatest lower bounds and least upper bounds, perhaps I need to make some sort of clever set where the number that exists that I get out of that is the number I'm looking for. And that's really what leads them down this whole path, yeah. Probably this is a bit ahistorical, because maybe in some sense you'd start with the square root of 2, and you'd discover the square root of 2 by studying some sort of sequence of rational numbers, and you could look at that set, and you could say, oh, the upper bound of this set is actually the square root of 2, or sorry, the least upper bound. And then you might try to generalize that idea to other square roots, right? But anyway, yeah. Okay, so we had a request to look through question 1 on the test. I think I'm just going to kind of write the set that we care about up here, because we're going to keep referring back to it. So they write this set, the x, the real numbers, sorry, this is an R, such that x squared is less than 19. Okay. All right. And the idea show, we're proving that sup a equals square root 19. I think that's the way this is all set up, if I recall. Yeah. Everyone happy so far? But that's just like the general idea of what we're doing. Okay, so they write out this proof, and basically the idea is you first sort of assume that sup A has to be kind of less than this, and then sup A has to be greater than this in some sense, and then you show that both of those kind of don't work, and so you get the thing you're looking for. All right. So part A, I think. So A was just, I'm not sure what I should do. Should I write out each part of the question? Because we don't all have the paper here, but on the other hand, we're going to spend a lot of time if I kind of write out every single question that we're asking. So is it okay if I say it in words? Or maybe you can share? Do you have it on the computer? And maybe you all can share? Do you have at least one?
Yeah.
Oh yeah, great.
Okay, excellent. Because that'll save us a lot of time. All right. So part A is just asking us to define what it means for a set of real numbers to be bounded above. I hope we're kind of happy with that. So we just write bounded above is equivalent to saying that there exists an m in the real numbers such that you could write like A bounded above or some B if you really wanted to say that it's really a set. There exists an m such that x is less than or equal to m for all x in this B. Okay. maybe you want to write that B is a subset of the real numbers. Sorry that I'm editing this at the end. This part isn't so important. We know what you're doing here. Okay. So everyone's happy with that. And then really the only hard part of part A was saying show that set A is bounded above. Okay. So again, like general tip, bounded above. If we're not looking for the least upper bound, go for something easy. Don't try to prove everything in the universe. Just try to find something that's definitely bigger. And let's see what kind of argument we're looking for. So what are the elements of the set? They're the elements that if you square them, you get 19. So we might suspect, perhaps maybe something like 5 is an upper bound. Is that right? Do we all agree with that? So we suspect maybe 5 is an upper bound for A. Does anyone see where I'm getting that? So if I kind of look at these, I'm like, what numbers are in here? They're the numbers that if I square them, I get something less than 19. So what kind of numbers can be in there? Okay, 0 can be in there. If I square 0, I'll be less than 19. What if I put in 2? If I square it, I'll get 4. What if I put in 4? I'll get 16. That's still less than 19, so 4 is in here. What if I put 5 in there? I square that, it's bigger than this. So 5 is not in there. And then I kind of start feeling, oh wait, but like everything bigger than 5 is also not going to work, right? You could even just take 10, like right off the start. If you don't want to try to think what's the smallest kind of integer that if you square it, it's bigger than 19, you just go like, what if 10 works? You put in 10, 100 is not less than 19, and all numbers bigger than that are also going to violate it, so you're kind of done. So how would we write that? We suspect maybe 5 is an upper bound for A, okay? So we'd say something like, let's look at the things that are bigger than 5. Suppose x greater than 5, okay? And this implies that x squared is greater than 25, which is greater than 19, okay? Okay, so, and maybe I'll write this on the next board. We basically have satisfied our definition because we show that every x greater than 5 is not in the set. So let's see, sorry, just a second to write that the most clear way. So x greater than 5. So we could just add here, implies that x is not an element of A. Okay. So then you could write something like x is less than or equal to 5 for all x element of A. That would be completely sufficient at that point. Maybe you could put a little a here and a little a here if you just don't want to have the same x's.
Jonathan, could you also have showed it by just how they defined A? Because I didn't specifically use an example like 5, but I just used it with how A was defined. Because
maybe you can talk me through that. So how would you do that? I mean, it might be possible. I'm not sure.
Okay. I'll talk through it like later.
Okay, sure, no problem. Yeah, and we'll see what all comes out because I mean there will be like sort of logically true arguments that will prove a lot of the stuff. So we'll see it as we mark it and stuff. You'll get your test back and we'll see. But yeah, we can talk about it after. But this is one way to approach it. It's probably going to be your fastest way, and it's going to be one where it's very concrete. You see, this kind of argument here is very concrete. And once we feel good about doing it, it's not actually computationally tough. It's just setting it up that's tough. Once we feel good about just saying, wait, let me just look at stuff that's bigger than 5, now squaring everything and just seeing that it kind of works the way we want it is not too bad. And I always, personally, like, I love to just pick big numbers. Like, I chose 5 here to show you kind of one of the easiest, smallest numbers you can pick. But sometimes when I'm doing something like this, it's like, find an upper bound, I'm like, let's just do 10. Let's just do 100. Just like, easy. Stuff that's easy to square, stuff that's easy to add together. Yeah. All right, so I think we should be satisfied with A. B. Do we need to talk about B? I think perhaps not. We have a definition for the supremum. We've all studied what the definition is, I hope. It's like, there are actually 2 equivalent definitions we've used, but yeah, the main one is just, explicitly writing out that it's an upper bound and it's the least upper bound. So if you pick any other upper bound, it has to be less than that other upper bound. So that's the definition of the supremum. So they're basically just prompting you to give the definition of the supremum. And then they say, how do we know that it exists? That's just like, well, you just showed that it's bounded above. So what axiom are we using? The completeness axiom, exactly. Okay, so C is now actually asking us to do something a bit more than that. Telling us to derive a particular inequality. All right. So, and that was what, inequality 3? No, inequality 1. Okay, so we just draw a line here. We are looking at C, and they ask us to write down alpha plus 1 over n. Yep. And remember, this alpha really is the least upper bound of the set. And we've already assumed that alpha squared is less than 19, but I don't think we need that for this inequality just yet. Right, so the first step is fine, right? You just square it. There's nothing, they literally just multiply it out. Alpha squared plus 2 alpha over n plus 1 over n squared. Okay, you can put the squared there. So there's no magic happening there, and then they're just asking, how do we get this this next inequality? And yeah, this is just one step as far as I can see, right? So they're just saying that, well, this is less than or equal to alpha squared plus 2 alpha over n plus 1 over n. Right? Is that what I see here in this so far? And then they just combine it. I mean, this step, just so it really looks like 2 alpha plus 1 over n. Okay, and we're all happy with why 1 over n squared is less than or equal to 1 over n. Is that fine? That's something that we've kind of slowly gotten comfortable with over doing limits. Yeah?
I really feel like this step,
yeah,
it's what they're asking us.
Yeah.
And they've just written from there to here.
Uh-huh.
So this step is what they're asking us. That's what's written out.
You mean going from here to here? No, you mean going from here to here.
Yes.
Oh, so perhaps your comment, now tell me if I'm wrong, perhaps your comment is, this is not a solution, I've just rewritten down what the test, yeah, no, that's correct. Okay, so what we would say, so we'd say y, sorry, that, well, because 1 over n less than or equal to 1 over n squared, sorry, no, that's correct, for all n. Oh. Right. and really that's enough. If you wanted to go further.
Is that enough? Wait, is that enough to show that
Yes.
so you don't have to show how you derived it?
You just showed.
Yeah, in this particular inequality, I don't think that there's anything more that you can show. There, in the next kind of version of this, when you're doing the suppose that alpha squared is greater than 19 much later in the question, I think there's a bit more you have to do. But yeah, in this one, I don't know what more you can say. If you really wanted to, you could do like this. You could say like 1 is less than or equal to n, which is equivalent to saying that like 1 over n is less than or equal to 1, which is equivalent to saying that 1 over n squared less than or equal to 1 over n. You see I'm just dividing and multiplying all the way. You can write that. I think this is unnecessary.
Yeah.
I think anyone who doesn't give you marks for this is being ridiculous. You're like,
So what I did was I just, I think that second equal sign, I just basically simplified it, but left the alpha and the other two terms simplified it to show that what's left is less than, then you continue from there with the because of what would be.
okay. I mean, if it's all logically true and you just kind of somewhere in there have this built in, that would be correct. But certainly for me, this is enough. Like we look at this and we're like, we hope you know that, and that's all that happened. I mean, how many marks did they give you for that? Let's see. Yeah, I mean, they gave you 2 marks. Maybe it's 1 mark. But that would be a good candidate where I'm sort of always saying, if you're not sure, raise your hand during the test. So that would be a good candidate where, like, if you wrote this, you could call the lecturer over and be like, because anyone who looks at that while you're writing the test is going to say, like, cool, it's not cheating to guide the student. Like, the student knows what's going on. They just need to know what we are actually asking. And that's fine. So this is a good candidate where if you feel like you haven't done enough work at this point, just ask.
Okay.
But that is fine. Okay, so let's move on. And then part D. All right, so what was this? Part D, we kind of had a hint. Anytime they're asking you, how do you know that a certain natural number, and they give it a little subscript 0, it's kind of, okay, so this is well ordering, right?
Is it well ordering?
Is it Archimedean?
Is Archimedean property?
Am I lying? Sorry.
Yeah.
Oh, well done. Yeah, so it is Archimedean. That's true. I apologize.
I think that's a trick.
Yeah, so I guess I would have been tricked. No, you're right. It is Archimedean. Okay, so I'll just say a completely different explanation. So anytime you see a natural number that's bigger than some real number, don't get confused by like a random combination of polynomials and stuff. It really is just a real number. You're saying there exists some natural number that's bigger than it. That's always Archimedean. Which I realize I've been misspelling in a lot of these. I watched some of the lectures. So that's embarrassing, but it's fine. Okay, so, and do we know how to state it? Do we feel comfortable with that? Writing down the definition, we all studied that, and we feel good? Okay. All right, so explain how 3 follows. This is that other inequality, I imagine. All right. Cool, so let's write it down. So this was part E now. Okay. And they are asking us to look at alpha plus. So we've already shown just in the previous part that you know, since in equation 1 we showed that equation 1 is true for all n, it's true in particular for this n naught. So we're just going to plug n naught into equation 1. Okay. So what happens is you get this less than or equal to alpha squared plus 2 alpha plus 1 over n naught, and we'll just say from equation 1. Okay. All we did was sub in n naught into equation 1. Okay. And then we have this other inequality that tells us something about n naught. And really kind of the pattern matching is you're just like, oh, that numerator appears in that other inequality I was looking at. So let's write that up. So we have this other inequality, 19 minus alpha squared less than n naught, okay? And so that's equivalent. So this is, sorry, right here from, and this was equation 2. We have this, and the point is you're just like, okay, I need to see what's going on here that matches up with this. So it's really the 2 alpha plus 1 is appearing there, so let's just solve for that. So, and you see that the n naught is in the denominator, so this is equivalent to just saying that 2 alpha plus 1 over n naught is less than, strictly less than 19 minus alpha squared. Okay. And then altogether, you can just write that alpha plus 1 over n naught squared is now less than or equal to, this is the way they presented it, yes. Are we happy so far? This one was strictly, right? Yeah. Did I miss something somewhere else?
Wait, not strictly. This one was.
Oh, this one we're just looking at this again? Yeah. Oh, wait, I see what you're saying. Sorry. Yeah, we won't use this. Yeah, you're one step ahead of me. That's perfect. Alpha squared plus 19 minus alpha squared. Okay, equals 19. Okay. And again, this might be a situation where you're like, have I really explained enough? For me, this is perfect. Instead of altogether, you could say, then combining equation 1 and 2, we have that. You know, you could write that. But for me, this clearly lays it out. If I'm marking this and I see this, I'm like, the student knows exactly what's going on.
Yeah.
They've looked at this equation, they've looked at this equation, they've rearranged this equation to get something that's in that equation, they've just substituted in, and everything's fine. So, so we're all happy with that. Okay, and then, so F, okay, so F I think we are also happy with, right? I don't know if I need to write that out. It's like, why is some positive number plus some other positive number less than or equal to the first positive number? How is that impossible? So how is alpha plus 1 over n naught less than or equal to alpha impossible? If you wanted to write out more, maybe I'll just give you something instead of just saying it all in words, but remember, you can always just like use the rules of math, right? So you can write this, okay? This is the thing that we want to show is impossible. And just in one line without really writing many words, you can just say this is equivalent to saying that 1 over n naught is less than or equal to 0, which is impossible. Right? I'm not saying that's the only way to kind of argue it. If you wrote like a sentence or two and kind of argued it, I think you'll probably get the marks, but I'm just saying that, do you see how this is very fast and like completely unambiguous? And we haven't broken anything. We've agreed that in this course, we've proven that I can always just add or subtract real numbers from, as long as I do it across any inequality. It's fine.
Can I add a line since and not to the element of the naturals?
Sure, yeah. If you say since, if you don't say this, you say since n naught is an element of natural numbers, that's also fine. That is exactly, like encoded in this, I know that, yeah. So either one is perfectly equivalent in the context of this question. All right, so G, we are now moving on to, I think, the second half of the proof. Okay, so we showed that the thing is impossible, and so our original assumption that alpha squared less than 19 was impossible. That's the whole point of the first half of the proof. Okay. Okay, so we are doing G. So G. Okay, and we need to derive inequality 6. Which is slightly more, just requires a little bit more of an argument than the one we did previously because we have minus signs showing up. Okay, so again, they just multiply everything out. So we agree with the first step, 2 alpha over n plus 1 over n squared. Okay? Yeah, I think I think we should be happy just dropping the 1 over n squared, right? Because it's just a positive number. So, so that's always going to be greater than alpha squared minus 2 alpha over n. Okay? Because, and again, you could just write, because 1 over n squared is greater than or equal to 0, either is fine. Maybe we should say, wait, let me just think about that. We may need that. We'll need that. Anyway, so this is fine. I don't think there's much more you need to say here. I'm not actually sure what more you could say. You'd kind of just be spelling out this statement with just lots of words. But we know this rule, that if this is true, adding this to the one side this statement follows that one. I kind of try to spell it out in words. See, even I'll probably make more mistakes if I try to describe it in words than use math. All right. So why does it follow from 6, this is part H, why does it follow that alpha minus 1 over n1 is an upper bound for A? Okay, so we've got a few steps built in here. Just erase a little again. If you wanted to write more here, maybe I'm being a little bit unfair. Like, if you wanted to write more here, maybe what you could do is you could say, because this is true and adding a positive number to this is always going to give you something bigger. I don't think that's necessary to write out that sentence, but if you did, you might feel better about it. You might just say like, cool, I'm describing what's in my head that I feel I need to say to finish this question and move on. If you feel better just saying that sentence and moving on, it takes you 10 seconds, then that's fine. Yeah. I don't think that's a bad test-taking strategy, but yeah. All right, so, sorry, we were doing H now. H, okay. And they're saying, why does it follow that alpha minus 1 over n is an upper bound for A? So let's see where they were. Why does it follow from 6? Oh, I think I kind of cheated you in the last question. Surely, right? Because, right, this isn't the inequality they asked us to study, sorry. Do you see what I mean? If we look closely. So inequality 6 is actually the one down the page. This was inequality 4, so I apologize for that. But let's see how many marks they allocated for the previous question, because I'm not sure if they want you to kind of talk through the whole thing. For G it was 3. Okay, so it wasn't that many. But okay, we'll leave this up here because you do kind of need it. Okay, so sorry, we're kind of repeating what we did in the first half of the question, where yeah, it's pretty interesting that they kind of broke it up this way. So I think that makes it a little unclear, because so me reading it myself, I'm not sure now if you would be expected to kind of restate that, you know, inequality 5 exists because of the Archimedean property. Okay. But okay, let's just write it all out. We'll write out like the most complete thing, and then we'll see what marks you get on the test by the memo. But okay, so this is fine. We're happy with this inequality. And there exists n1 such that, and they're telling us that it's 2 alpha squared minus 19, and this is less than n1 by the Archimedean property. Okay. And you could even at this stage say, well, that's, as we did before, that's equivalent to saying that 2 alpha over n1 is less than alpha squared minus 19. So this might be a good candidate for where you put a star in your test paper and like a star number 2. Sometimes you'll do that. So you'd write, so by combining star and 2 star, or star number 2, alpha squared minus 1 over n1 squared is greater than alpha squared minus 2 alpha over n1. Okay, so I'm just substituting in for n1 now, which is great. Is everything fine? Sorry, I just want to check this very carefully before I do it. Oh, because we have a minus sign. Is that what's going on? So what you might want to do here to make it completely clear is you might want to, I probably, if I was doing this right now, I would put the minus sign in at this stage. I'm so sorry if that messes up your notes, but, or you'd add another step. I kind of wrote it here, so I'm not going to add it, but what I would do is I'd put that minus sign there, put that there, put the minus sign there, okay? Sometimes that's a technique to avoid kind of messing up, like what am I doing when I have negatives and positives and stuff? Just put the minus sign in, because then you know you're just dealing with this object, and you have that same object right here, so you don't have to think, okay? Minus, okay, and then that just equals to 19. We all happy there? I think we now avoided any errors. A lot of this is actually setting yourself up not to make mistakes, rather than worrying about whether you're perfect at making mistakes or not. Try to develop the techniques that avoid little silly things. Okay. So we were happy with G now. That was all G. Okay. So now we talk about H. Okay. So why does it follow that from 6 that alpha minus 1 over n1 is an upper bound for A? Okay, so we just need to quickly work on that. Let's just cross this out. Okay. So they're really asking us, why does it follow? They're asking us alpha squared minus 1 over n, 1 squared greater than 19. I'll just write it there. Implies that, alpha, that implies that this is an upper bound for A. So is this true? Did I leave out an alpha somewhere?
It's just alpha.
Oh, true. Sorry about that. It's that thing in the brackets. Yeah, this shouldn't have been squared. This shouldn't have been squared. Wow. How long has this been going on for? Very good. Okay, we're good. Yeah, these things happen. All right, so why does it follow that this is an upper bound for A? So we want to show that if I take any x greater than or equal to this, then it's not an A. That's one way of going about it. So we'd say something like this. Suppose, this is kind of like a proof by contradiction. Suppose x is greater than or equal to alpha minus 1 over n1. Okay. Then that implies that x squared is greater than or equal to alpha minus 1 over n1 squared, which we showed is greater than 19. Which implies that x cannot be an element of A. So every single x that's bigger than this number cannot be an A. Okay? That's probably, I would think, the fastest way to show that. It's maybe getting a little confusing over here, but this A is really with that sentence. Okay, any questions on that? This one's, again, like, it's kind of like a proof by contradiction, I guess you'd think of it. Suppose, just consider the ones that are bigger than that. So it is kind of a proof by contradiction. You're saying, like, you know, if this thing really isn't, if it failed to be an upper bound, then something should go wrong with this argument. But okay, are we kind of happy with why that's true? Okay, so let's move on. All right, so then we have I, and then they say, why does this contradict our choice of alpha? Right, because, well, I think so the point now is we said that alpha is the least upper bound, but we just showed that this thing, or this number, is an upper bound, and it's clearly less than alpha because this is some positive number that we're just subtracting off. So I can write that out. Do we need to write that out, or does everyone kind of understand that? You just say that, like, you know, this is less than alpha, and we showed it's an upper bound. But alpha was supposed to be the least upper bound. So, okay, and then J. J is probably one of the harder ones. We discussed this a bit on Saturday, us two in the middle row. So, it's not really hard, but you may feel uncomfortable answering it. Because we haven't focused so much on sort of the foundational issues of, like, constructing the real numbers, but really you want to say something like, we don't know that the square root of 19 exists as a real number because so far we've only discussed certain properties of the real numbers, like kind of the field axioms, the ordering, the completeness axiom, the Archimedean property. And none of that guarantees us right away. It may not be obvious that that guarantees us that square root of 19 is a real number. Now, how do you kind of answer that in a concrete way? Well, I've seen the memo for the test, and yeah, I wouldn't say that it's the most illuminating answer that was written in the memo. Not that it was bad or wrong or anything, but it just kind of says, like, oh, we didn't know that this number existed yet, so therefore we didn't know that it existed yet. So I don't know if that's convincing. But yeah, I don't know how much we should go into that. So there's sort of two things built into J. So your one question might be, how do I answer a question like this on the test? And your other question might be, what is the answer to this question in terms of mathematics literally, like actually knowing the subject? The answer in terms of knowing the subject is like, we've tried to build up the real numbers, or we've tried to build up some number system using a minimal set of properties. We've tried to say, like, what are the minimal set of properties that we're going to use, and then what properties does that, or what sort of things are true about the number system that we build with those rules. And we've slowly but surely kind of showed that this number system that we build, that we call the real numbers, has all of the kind of properties and all of the numbers that we're used to using for, like, all of our lives and all of these subjects. how should I kind of write this on the test? I think I would just say something like, maybe I can write out a sample answer. Yeah. I think saying it in words a second time is not necessarily that useful. So I also see, yeah, and they gave you 1 mark for it, so maybe that kind of telegraphs that you don't need to write like a giant paragraph. So maybe that's why the kind of thing in the memo was so brief. But I would say something like, so far we've only shown that the real numbers are a field. Okay, you may not have covered this yet, so what I mean by that is have addition, multiplication, and division, and technically the distributive property, but I don't think anyone will fault you if you don't mention the distributive property in this course. So we've only shown that the real numbers are some number system that has these ways of combining the numbers, like addition, multiplication, and division, that the real numbers contain, and I want to save space and time now, so I'm going to start using symbols. I should have just used R. Contain Q and have, and now shown is kind of probably not true, but anyway, it's fine. And have the Archimedean property, the completeness axiom, and ordering with less than or equal, etc. Okay. And then I would just say, like a kind of a final sentence. Now I think this is overkill for this answer, but I'm just kind of giving you the way that I think the answer would be written. So just say like, none of this, guarantees square root 19 is a real number until we use these properties to check. So that could be like one sort of way. It's sort of the idea. It's like we wrote down a bunch of abstract properties, but did I ever mention square root of 19 at any point when I told you about the completeness axiom or about any of that stuff? Not really, right? So we just said like, let's have a number system that has a certain set of properties, and now we're showing you that there really are all of these familiar numbers that we've been using really are real numbers. They really are in this number system that we built. Okay, but I mean, you see I wrote quite a lot for like 1 mark, so if you wrote something less, that would probably be fine. And then part K was just asking us, why is alpha not equal to minus square root of 19? Okay. There are a number of ways that you could kind of argue this. Probably the quickest way to argue it is you want to kind of like use the fact that these are positive numbers. There's some kind of positive numbers floating around. So you could say something like, well, for one, you could just like, I wonder if they did this in the memo, sorry, I'm just thinking in my own head. So you could just go for like a contradiction, right? You kind of have a picture in your head of what's going on, hopefully. It's like, we built this list of numbers that are like bounded above, with the least upper bound being square root of 19, like if I'm going along the number line. So how could this thing weigh on at minus square root of 19 be the least upper bound? Well, one way to violate that would just be to find something in the set that's just bigger than square root of, or minus square root of 19. So you could just say something like, 1 is an element of A, because 1 squared is less than 19. I think we agreed that was the definition of A. I actually said I wouldn't erase it, but I did. Yeah. So, but minus root 19 is definitely less than 1. So minus root 19 cannot be sub A. If you wanted to say in parentheses, it's not an upper bound. Okay, it can't be the least upper bound because it's not even an upper bound. All right, so are we happy with kind of question 1 now? Any kind of lingering things despite us going through the whole thing one by one? Is there anything kind of left over that we need to do? Okay, cool. Let's see. And we're happy with kind of the broad picture of what we're doing. Yeah, okay. So what should we talk about now? I do have a counterexample for 2C. That was one a lot of people were kind of interested in. This one's a little bit harder. This is probably the hardest question on the test. Maybe not. Maybe, like, it's hard to say, because, like, if the counterexample just pops into your head, then it's an easy question. You'd just be like, oh, fine, and you'd get stuck on something else and focus on that. But if it doesn't pop in your head, you might find it to be the most frustrating. So if I just say it in words, can you think of irrational numbers that if you add them together and you multiply them together, you always get a rational number? Because that would be one way of disproving it.
Not if they say positive irrational numbers.
Yeah.
The fact that they say positive is like that.
Right, because our first thing we always use to check these is we go like square root of 3 and minus square root of 3, right? Yeah. So what could we do if, so I'm gonna tell you it's false. Unfortunately, if that's ruining any lives, sorry. But so.
Put it to a true.
Sorry?
What does the memo say?
It is false.
And A and B?
A is definitely true, right? That's just field axioms. B is yeah, that's definitely true, right? You can prove that immediately, right? Because you have A element of Q, B element of R without Q. You look at, suppose A plus B, that's really a plus B is an element of Q, sorry. Right, it was A plus B.
Yeah.
So A plus B equals to like some C, but that implies that B is equal to C minus A, which is an element of Q contradiction, right? So that's fine. So we know the answer to that. But, all right, so what can we do? So this was B, for anyone who's watching the recording. So for C, it is false. So the question is, can we think of irrational numbers that if I add them together, I get a rational number, and I multiply them together, I get a rational number, and they're both positive. Okay, so how could we do that? So what are our favorite irrational numbers? Let's just list some out. Square root of 2 is a good one. Probably throw in square root of 3 too. And we do plus or minus, so those are our favorites. We've got E, right, pi. I always tell everyone, try these out if you ever need to do something. What else could we make that are irrational numbers that are still kind of simple?
Thing is, like, I've seen the solution.
Oh, you've seen the solution. Okay, so well that's fine. All right, so what if I A plus B root 2
Yes, it's
plus or minus? Okay.
That's true.
Yeah.
and so.
And what's the easiest one we can pick here so that both plus or minus are positive? You could go to say 2 plus or minus root 2. Okay. Those are all positive. And then if you multiply them together and if you add them together,
I also feel like we can.
that's a bit tricky. Sorry, you feel like you've been like wronged. You're like, I was cheated by this
Honestly,
test.
my issue was when I proved it,
It felt like it
I knew
worked.
they needed, like with C, I needed a counterexample, but when I was proving it, it felt like it worked because I couldn't come up with a counterexample.
Fair enough, yeah. No, I sympathize a lot with this. This is one where it's a bit funny. Like I say, like if it just popped in your head and you tried something and it worked, you'd feel like you probably wouldn't even think about it. You would move on, hear other people complaining and be like, what? If it didn't pop in your head, it's very frustrating because this is more a problem where you'd want to go home and think about it.
Yeah.
So it's a bit rough, but it's it's worth like what 2 marks out of 50, so it's not the end of the world. But yeah, so I sympathize with that. It's really just a kind of a yes, no, and what can happen. So maybe maybe the lesson going forward is we're gonna add to our list of favorite irrational numbers this one as well. And to be fair, like I haven't really emphasized this to people in tutorials. I always tell everyone check these. So this, when you want to check out something, maybe just check a quick one like 1 plus or minus root 2, 2 plus or minus root 2.
I feel like
Yeah.
the examiner, he said, like, if you answered B well, you
Uh-huh.
can answer this one well. Because if we state and understand B, it also gives us the hint to use this kind of rational number.
Yes, perhaps. Yeah.
Yes, if we.
Perhaps there's a
Let
hint
it
built
be
in there.
and-
It would be hard to read into that though, because if it wasn't that
Then,
way,
yes, that's the
yeah.
thing.
But I hear what you're saying. In hindsight, yes, and people do write tests that way sometimes. But if they don't, then you don't. You're like, how do you know?
So I can propose that quickest solution. It follows from B. Then
Well, it
so from
doesn't.
B, I can
It
have
doesn't
this,
immediately.
I can have this rational number. Then I do the math. Yeah, but it's just.
Yeah. But there is something built in there where like maybe you're just looking at it and they're trolling you a little bit like there's an A minus B and an A plus B, perhaps we should be adding these or multiplying them. Yeah. All right, but we see the solution, so there it is. Save it for a rainy day when the exam comes. We know that these are good things to check too. All right, so do we want to do 3? I know you wanted to talk about 3.
Yeah.
Does anyone else want to talk about 3? You also want to talk about 3. Okay, so let's do 3. This is similar to something we did before, but I think it's worth it to just do. If we could probably just go through it a bit faster than we have in the
Yeah.
past, but I think it's always worth it to do these.
Because my rough work didn't work out, eh?
It didn't work out,
And
yeah.
what I did is, like, I wanted to use one of the methods that we used to prove the
The denominator bound, yeah.
Yeah.
Yeah, that's where it can go wrong. All right, so let's do that quickly. All right, so and just to say, we have about half an hour left. So are we okay with kind of doing this for 10 minutes?
Yeah.
Okay, so we're not going to feel cheated that we didn't get more serious. There's always time for more serious.
Yeah.
All right, so we're looking at question 3. Oops, that's not how you write a 3. And they tell us to show that the limit. Do they tell us something? Yes. So they say that AK goes to 3. Was it?
Yeah.
Good. And then so does that imply that the limit as k goes to infinity of something that I can't remember, 2 alpha k minus 1 over 3 alpha, why am I doing alpha, ak plus 1 equals to a half, okay? And we know by now that the first thing we do is we got to just simplify. So what are we looking, or we're going to write down the thing we're looking for, 2ak minus 1, 3ak plus 1 minus a half. This is the thing we're looking for. We want to somehow show that there exists a capital N such that for all the k's bigger than that, this is true. And then we want to simplify this. So, you know, we're going to just cross multiply, or however you think about it, common denominator. So I think I'm just going to do this. You'll believe me in a second. So 4ak minus 2 minus 3ak plus minus 1 over 3ak plus 1. Okay? So I'm really putting an equal sign there. Okay, there was a 2 in the denominator, I just kind of factored it out. Okay. And that equals a half ak minus 3, okay, over 3ak plus 1. Do we all agree so far? So at this point, we can even just kind of jump ahead and say that this is always I really want to simplify as much as possible because I don't want to do any other work. So we can do that right away. Do we agree with that? If you wanted to think about it in steps, I got rid of the half. That's kind of obvious. It's less than or equal to this positive number without being multiplied by half. I dropped this from the denominator. That's always useful. We've seen that technique a few times. And then I kind of now, once I do that, I have a third sitting in front, so I can drop that. Or if you want to go all in one step, you could just have a 2, you could have like a 6ak plus 2, and you could just say, I know that's less than or equal to ak. That you may feel less confident about, so it's nice to think about it in steps. It's nice to just say, I can throw that away, I can get rid of that, then I have a third in front, so that can go away, and so I just have an ak. Okay. Some of this isn't even needed. You could still have constants in front and still prove everything, but I'm just saying this is a lot easier to look at. This one we know we feel confident about, so it's really resolving that. And there is kind of a interesting thing that arises now in terms of test-taking strategy, because perhaps at this point you could say, well, we have a lemma from class that tells me what this does, this 1 over ak, and just write that, and then go there if you've memorized the result. I don't know if I recommend that. If you find yourself really short on time, then strategies like that are useful. I don't think I recommend that because it like I say, unless you're writing the style of test where it's like a billion questions and you need to answer each one really quickly, then you memorize stuff like that. For this, you have enough to memorize already. It's already a lot. And on top of that, it makes you ill-equipped to deal with questions that are slightly different.
Yeah.
You don't want to get thrown as soon as you get a curveball.
And the problem with that lemma, isn't it that we would need that in the denominator, the limit of the AK has to be there somewhere?
The limit has to, what do you mean?
With that lemma, the limit that it approaches, shouldn't it sort of be incorporated somewhere in that thing?
Oh, did you have like a -3 in here?
No, I mean like if we wanted to use that lemma.
Did that lemma have a -3 in here?
Well, the way we did it in class, it sort of like it was Bn, the sequence was Bn, and its limit was incorporated in.
We end up using its limit
Okay.
to resolve this, so maybe that's what you're remembering.
Okay.
But it will work for something
Okay.
1 over AK. But yeah, but we have the limit. We have that the limit is 3.
So, yeah.
Yeah. So, but it is a fair point. Like, sort of just slight variations might throw our whole thing. So let's just go through it. It's also good to understand it because perhaps they give you that lemma in a test or an exam, and they say, "Please explain what's going on here," and it's like, "Oh, crap! I just like memorized the lemma because So, all right. Now I'm just looking for chalk, kind of destroying all the chalk. Okay, so this is kind of like a side. Resolving the part of the inequality 1 over mod AK. Right. So recall the reverse triangle inequality is key here. Is key. Okay. And we talked a little bit about this. I can say that again. I don't know if we kind of all remember during our hectic kind of test preparation. But I did kind of mention this before, that the idea is when you have something in the numerator, we have some hope of using well, here it's obvious what we need to do because we just have the limit appearing of the original sequence. And so we have some hope of resolving it. If we had something slightly different in the numerator, we would still feel like we probably just need to use like the triangle inequality or completing the square or doing something clever using the original limit of the sequence. But when we have something in the denominator, asking me to have like 1 over mod AK less than some, say, C, is equivalent to saying that I need to now find some C that is less than, 1 over C that is less than mod AK. Okay? So now we're in the realm of looking for things that are less than mod AK. Whereas when we're studying stuff in the numerator, we're looking for things that are greater than. So that's why I was sort of trying to link that up. It's like when I need to do this, the reverse triangle inequality helps me. So try and match that up. Reverse less than, like, okay? But let's actually recall what that meant. So once you kind of just have that memory, I need to use a reverse triangle inequality, then the first thing you do is just write it down. Like, don't try to remember the whole argument, just write it down. So we just write down mod AK minus 3. That's the thing we have. We're given that. That's some, like the limit and the sequence. Okay. And then the reverse triangle inequality gives me this. Minus mod 3, and okay, that's positive, so it doesn't do a lot. Okay. Okay. I'm gonna plan out this board space well. And we knew that we could choose some epsilon to make this, like we can put anything here. So we're going to put our C here. And maybe I'll just kind of like write this. We can choose N1 to make, sorry, that's probably not the way you want to say it. We can choose C, and there exists an N1 such that K greater than N1 makes this true. Okay, it's kind of the way we're piecing it together.
Would we have to say that C is equal to E in this case?
Not necessarily.
The epsilon in this
Not
case?
necessarily.
Okay.
We haven't worried about that yet.
Okay.
Okay, and that's why I purposely just want to choose a C. Because I don't want to get wrapped up in multiple epsilons, or is it the same? Certainly that's in the back of your mind. But for the moment, we just know that sort of the logic is like, I can just pick this number, and whatever it is, because this sequence converges, there exists a capital N such that for all the little k's greater than that, capital N, I get this.
Yeah.
And so anything further that I do is fair game. Just trying to think how much of this I should keep. But actually, perhaps we should ask to book a slightly different venue and have more boards. This will be all right. I'll just rewrite it. But the point is, for starters, you're just kind of writing down what kind of stuff you have available to you. So you know that you can write this, you know that you can make it less than some constant, and you know that by the reverse triangle inequality, which you were hinted at you might need to use, this is all kind of possible. We haven't firmed it up yet, we haven't written our proof out, but this is all like kind of possible. There's some way for me to get an inequality chain that looks like this. Okay. And then we just kind of simplify it more. So what does this give us? It says that minus C is less than mod AK. Because remember, I want to find something less than mod AK. That's what I said right here. Right? I said I want to find something less than mod AK. And okay, probably is a bad idea to choose these both being C, but it's fine. So we need to find we need to study mod AK. So we remove the absolute values by doing this, by putting minus C less than what was in the absolute value, less than positive C. Okay? And then that's just equivalent to saying that 3 minus C is less than mod AK, which is less than C plus 3. Okay? And this is the part we care about. That's what we care about. Maybe I'll underline it a little better. We care about this side of the inequality. Because remember, I was saying we just want to find some kind of number that's less than this, less than mod AK. And so we see that actually, if we choose C equals 2, this implies that 1 is less than mod AK, which is equivalent to saying that 1 over mod AK is less than 1. Okay. Now, probably want to draw your attention to something here. This is just kind of for the purpose of your notes. I think we're all sort of on the same page, but I did kind of use a C here, just saying we're kind of looking for this. We're looking for some constant that's bigger than this, and that's equivalent to saying that 1 over some constant is less than this. It was probably a poor choice to use C here, because as you see the way that it worked out, we didn't really get a 1 over c on this side. Those are kind of unrelated. But this was just like a sketch of what we were hoping for, and this is the actual thing that happened. Okay? So just so we're all on the same page, you may want to make a note of that. I realize that maybe if I give this talk one more time, I'll choose different constants or something. But part of doing it, part of leaving the c undetermined, the power, if you look in your textbook, they don't leave the c undetermined. At this stage, they make this argument and they write down exactly a clever choice of c, and it works well. But then perhaps it gets you into difficulties if you had to do something slightly different using the reverse triangle inequality that wasn't this argument. So I really want you to see that the point is, because this sequence converges to 3, you can pick some constant here as long as it's positive. And you know that there's a capital N, and then you do your whole max argument where you make 2 different inequalities true at the same time. So we're fine. And then when we get to this stage, you get to decide, but just make this positive, whatever it is. You get to decide. You could choose c equals 1. You could choose c equals like pi over 2. I just think that it's really nice to choose c equals 2. Because, well, you can see, we get 1 over mod ak less than 1. Okay. From this point on, do we think we can do the rest of the question? Does anyone want to see the rest of the question? Because I think you know that there exists a capital N1 such that this is true. That's what we've given you. You can now say there exists a capital N2 such that this guy is less than some epsilon once you're given that epsilon. Okay? And then you just go max, and as long as we're past the max, or we're at the max or greater, both statements are true and your whole inequality works because of the reasons you have in your notes that we wrote down but are now erased. Okay, so I suggest, I don't think we needed anything on question 4, right? Question 4 was almost exactly like the tutorial. Just kind of like you could use induction or you could do some other arguments to do pretty much each of the pieces. All right, so let's chat a little about series, I think, with the last 15 minutes, unless there's any other questions on the test. One thing I'll say is, just like sort of a 2-minute speech on the test. If you're unhappy with your results of the test, I haven't seen, the results are not done, we're not done marking them. If you're unhappy, don't beat yourself up. Typically, real analysis is quite a steep learning curve, and then it levels off. It's really common for people who do very well in the course to not do well in the first test, do better in the second test, even do badly on the second test, and like ace the exam. The reason for that is, as you can see, these sort of arguments feel very, very unfamiliar. And then once they are familiar, it's like almost, how was I not able to like add numbers to an inequality, for example? That may have seemed weird at first, and now it's sort of like really easy. So a lot more of what we do for the rest of the course is just going to be like similar to this, with slightly different definitions and slightly different goals. And at every point we're going to be doing the same thing though, like here's this formal definition, here's the thing that we were trying to achieve, here's a picture that explains why the formal definition and the thing we were trying to achieve are the same thing. And now here are some examples of how you actually calculate stuff with these kind of theorems and definitions. So anyway, so don't beat yourself up. If you don't like it, if you did well, then that's great. But yeah. Okay, so yeah, so let's talk a little bit about series. Just kind of the series examples we've had so far. Everyone was done writing this down. Oh, cool. But yeah, just the last thing. So the worst thing to do would be to feel bad about your mark on the test, feel you should have gotten 100% and you didn't, or feel you should have gotten a really good mark and you didn't, and then work less. That would be the opposite of what makes sense. So don't kind of beat yourself up. But I think we were reasonably well prepared for this. Yeah. Okay, so I think what's useful is to kind of look at like, maybe we should look at tutorial 6, but perhaps I should give you a sketch of what to think about when you get a question on series, right? Okay. So what's the best way to represent this? Okay. Groups. Wait, let's just think about what the right thing is to call this. Okay. Sometimes it's useful to just write the title of the section. Okay, so series. So we'll just write like types of questions. Okay. This is not really intended to be a list of every type of question that you can get on series, but the point is there's like two broad classes of questions that often come up. So the first one is said like calculate the result or should I say limit? Calculate the result of an infinite series. Okay? So this is, any of the variety of ways of saying, please find me the number. Like literally, you're given this infinite list of numbers, add them up, tell me what the number is. Find the number for me. So that's a very specific question. It's saying calculate. We need to literally do something to get that number. And so you want to think, what techniques are available? Okay. So first off, so I would say first off, the definition. Limit, sum this series from k equals 1 to infinity is defined as saying take the limit as n goes to infinity of the sum up to a finite k of that sequence. Okay, that's the definition. That's what we mean when we put infinity there. We mean calculate this, take the limit. Okay? So why am I writing that? Well, one, it's just good review, but the point is that really tells you what you need to do. You need to calculate what the partial sums are. In other words, I need to find an expression for that sum up to a finite n. Okay, so we must find an expression for Sn, and maybe I'll just really emphasize, for the sequence Sn defined as that finite sum. Okay. Okay. We're running a little low on the white chalk. Maybe we'll just use yellow. So many boxes. Let's see. Okay, we'll just use the yellow chalk. So how do we find an expression for the partial for this sequence? Okay. So you have some different techniques. So one, is it a geometric series? If you can manipulate it into a geometric series, you're basically done, right? In fact, you probably have memorized the expression for the sum up to infinity, like without even worrying about the partial sums. But you might be asked to write down what the partial sums are. So make sure you can do both. if it's not a geometric series, what other things can we do? We've seen telescoping coming up. Telescoping. Okay. Hint. Does k and k plus 1 appear? So if you see k and k plus 1 both appearing in your sum, it's not a guarantee, but it might be a hint that maybe there's some way of rewriting it as telescoping. And I could also say arithmetic series, but I think we haven't covered that, right? And I don't know if we will. But that is something to keep in the back of your mind if you're ever in another course. Arithmetic series, we certainly have a formula for that. We can derive a formula for that, so that's a way of finding impartial sums. I guess we're probably not going to do it because it probably doesn't converge. But that's fine. Just be aware of that. And then, what's the more sort of broad third idea of what we do? Find the formula for Sn. Write out some terms. Okay. But what if I'm asked to prove? What if I write out some terms of this sum and then I don't know if I'm right, that the formula that I had? Well, you might have some clever way of proving it, maybe with like monotone convergence or something like that. Or is that even true what I'm saying? No, that wouldn't even matter. But the point is your general go-to. Prove with induction. That's always going to be useful. Induction. Right? Because this is something that inherently depends on n, on natural numbers. So induction is available to us a lot of the time it's going to be useful. If you can get that formula of what you think it is, you may have seen this in some of the tutorials, right? Or some of the exercise sheets. Like once you have the formula, proving that it's the right formula is not too bad. It's like getting the formula that's the hard part. So if you can guess what the formula is, and you're not sure, just try prove it with induction. It's inherently provable with induction because we're depending on n. And the other thing is series work really well with induction. Because remember what your induction hypothesis is? You're like, assume Sn equals something, a sum up to n of something. And then you need to now show what Sn plus 1 is. And Sn plus 1, you write the formula on the left-hand side, and then it's going to equal a sum from k equals 1 up to n plus 1, which is just equal to the sum from k equals 1 up to n plus the a n plus 1 term. Which is, so you've got your induction hypothesis, which will fill in the sum up to n, and then you just add on that other term. So you're basically literally going to be like adding two things together and showing that they're equal to the formula where you plugged in n plus 1 on the left-hand side. So it's a lot of words. I don't think I'm going to write that all out. I think that's kind of obvious, but really mostly made obvious by doing some examples. And to be honest with you, I think this is where I would stop unless we really cover a lot more on this. If you're asked to calculate the actual number that a sequence converges to, or an infinite series converges to, you really don't have that many tools. And you want to feel that way. It's good to feel like you only have 3 or 4 tools, because then you don't have to remember a lot. You just check. Check this one. This one's in or out of the window immediately. Like, you'll see whether you can rearrange it into geometric series or not. This one's a bit harder, but you may see it. If you don't, go here. You know? Try see if you can get a formula, and then maybe you can prove it with induction. Okay. And then the sort of last 2 minutes, I'll just say the other one. The other one is not calculate the result. It's, you know, just show does it converge or diverge. So this is still sort of under the heading of types of questions. 2, does sum up to infinity of k equals 1 of ak converge, or diverge. Okay? And then what kind of tools do you have available to you there? Again, you can always